Hey everyone, welcome back. Last time we spoke, we were on chapter 4 um, on carbon and molecular and the molecular diversity of life. We did part of this chapter, and I'm actually going to let you work on the rest of this by yourself. So just reading over the material and also working on the study guide. It's pretty much background, and we were going to come back to all of this in more detail. So I'm going to let you, there's not too many slides either. I'm going to let you look at those. Do remember that you need to remember um, for a quiz, you need to be able to look at a diagram that is showing you the different functional groups. So, for example, showing you OH, so make that a little bit bigger here, our hydroxyl group, um, being able to say, hey, yeah, that's hydroxyl, okay? Or if I give you COOH, saying, yeah, that's carboxyl, okay? It's a matching quiz. Once you have these groups down that are on this diagram located in figure 4.9 in your textbook, chapter 4, you should take that functional group quiz. And I think I mentioned last time that you can obviously look up the answers, but you really need to know these functional groups because they will play a role in the next chapter we're going to be talking about. And once you get into bigger macromolecules, you have to know what those functional groups are because you need to, in order to know what the macromolecule is, you need to know what the functional groups are. So just a warning about that. Um, so I'm gonna, like I said, let you look at the rest of chapter 4, and I'm gonna move right into chapter 5, which is really a big portion of this unit, as well as water that we've already discussed. First of all, there's lots of molecules that are big, and they're called macromolecules. The ones that we really care about are carbohydrates, lipids, and proteins and nucleic acids. Those are the ones that we're really interested in, and we're going to talk about these extensively throughout the course. So understanding these molecules up front is going to be huge towards being able to do well in the course. So let's look at these in one after another. Oh, sorry, forgot that first of all we need to talk about building blocks. So macromolecules are called polymers, meaning they're many units, poly meaning many, and they're built up from these things called monomers. So monomer is going to be a repeating unit that serves as a building block for these polymers. Okay? Carbs, proteins, and nucleic acids are all considered polymers. They are made up of smaller individual building blocks called monomers. And for each one of our macromolecules as we go through this, we're going to talk about what the monomers are that make up each of our macromolecules. Okay. One of the questions that sometimes students ask is, what's the relationship between a macromolecule and a polymer? And they're basically the same thing. Okay. Polymers are big repeating units, molecules that have repeating units, and macromolecules don't necessarily have repeating units, but they're also large molecules. They're going to be made up of many repeated units. They may have a little more, they may be a little more specific and not just have repeating units. So they might have a functional group added onto them as opposed to a polymer that might just be many units altogether. But you will not have to make a distinction between a monomer and a macromolecule. Okay, so if I have a huge molecule, I have a huge polymer, how do I break it down? Well, we're going to talk more about these throughout the course. There are these special molecules called enzymes, and these are they're actually proteins. We'll talk about that a little bit later in the unit. But enzymes are proteins. And if we want to make a polymer, if we want to build up a polymer from monomers, we're going to do something called dehydration synthesis. What does that mean? Well, synthesis means to make, and dehydration means to take out or remove water. Okay? So that's if I want to make a polymer. I'm going to have a series of dehydration synthesis reactions to make a polymer. Opposite is called hydrolysis. In hydrolysis, we break a polymer apart, and that is lysis, means to split, and hydro again refers to water. So what we're talking about with polymer, with hydrolysis, is making a molecule smaller by the removal of water, by adding in water. So we're using water to split the polymer into smaller pieces. One of the things that I'm finding kind of hard with doing these lectures is I don't have feedback, so it's up to me to realize when I make a mistake, and sometimes you don't always know that you've made a mistake. So if there's anything in the lecture that's like, you said this, let me know, because I may have said something by accident incorrectly. I think for the most large portion, I'm fine, but like I said on that hydrolysis one, I just misspoke. So if something doesn't sound right, please let me know and get back to me, and I'll get back to you, and we can figure it out. Okay, so here is a dehydration synthesis reaction. We're making a polymer. We're taking a monomer here, and we're adding it onto a short little polymer. And when we do that, we're going to remove an H from one side and an OH from the other side. Okay, so a hydrogen atom is going to be removed, and a OH. Remember, OH is hydroxy. So we're removing a hydroxy from the other. And in doing that, we're removing doesn't actually show this completely, we're removing a water molecule. Okay, and we're making a longer polymer. Hydrolysis is the opposite. We're going to break something down by putting in water to split the molecule apart. So we're going to take that and we're going to split it apart. That's just the reverse. Now we're adding in water. And now we've got our smaller polymer and our monomer. Okay? So that's the two types of reactions. All these macromolecules we're talking about, they are all made with dehydration synthesis. They are all broken apart with hydrolysis. I'm going to skip over that video. Feel free to watch it. It's just going to explain a little bit more about polymers. There's lots and lots of polymers that can be made from a small set of monomers. Think about it this way. If I have the alphabet, there's 26 letters in the alphabet. How many words can I make with 26 letters? Well, the answer is there's an endless amount, right? Obviously, I'd have to make the words bigger, but I could just keep adding on letters and making longer words. Okay, so the cell has thousands of different polymers that it uses, and those are the ones that we're interested in because those are our macromolecules, because those macromolecules are found in living things. Okay, and we're going to talk about 4 sets of macromolecules. The first one is going to be the carbohydrate. And I think this is the one that's most common to students who've had biology before. Carbohydrates are things like sugars, so just your simple table sugar, and then also polymers of sugar, which would include, sorry about that, things like, come on, go away, would include things like starch. So starch would be an example of a polymer of sugar. The simplest carbohydrates, remember we talked about what a one unit, one building block would be, and we said it was a monomer. And the monomer of a carbohydrate is called a mono. And then saccharide, and saccharide refers to sugar. So we're saying here that it's one sugar. Okay. The simplest one you can have is a monosaccharide. That would be your building block for carbohydrates. More complex carbohydrates are polymers, and as such, they are called poly because we've got polymer, and then we've got sugar again. Okay, so we've got many sugar units. Okay. So you take a bunch of monosaccharides and put them together, you have a polysaccharide. So sugars, monosaccharides, like I said, are the simplest, and they are typically found in the formula 1 carbon. Oops, that was not what I wanted to do. Of 1 carbon to 2 hydrogens to 1 oxygen. Okay, so referring to that C, H2, and O. The most common one that you're going to find is, as I said before, glucose, C6H12O6. You should be able to recognize this. So if it comes up on a test, you should be able to say, yep, that's glucose. And that's important because glucose it's kind of like, how a car needs gas. Our body needs glucose. And we don't straight up eat glucose usually, although we can. But the vast majority of our energy that our body uses is converted first into the form of glucose before it is used by our body. So we need to know that one for sure. Okay, though they're often drawn as linear, sometimes sugars can form rings, and I've actually got a picture of that. We're not all that interested in that kind of thing right now, but let me just touch on this other sentence here, and then I'll show you a picture of the rings versus the linear models. So monosaccharides serve as major fuels. That's a huge, huge thing. Okay, so they're going to be our primary energy source in our body for everything, for building muscle, for thinking, for breathing, etc. Okay, here is talking about the shapes that sugars can take. So the one up here at the top, that's a linear shape. But notice how it can also be that. Okay. Also note, and this will be important for later on, that here at all the vertices, so all the angles here, I'm showing carbons. And then there's another one up here. That's my first carbon, second, third, fourth, fifth, and my sixth carbon. Typically, they're not, that much detail is not shown on a molecule. Instead, here they are just showing the 1, 2, 3, 4, 5, and 6. So they're only showing those letters. Now, even more or even less detail than that, sometimes they won't have any of that detail. They'll only have you just have to assume that whatever is at that angle is a carbon molecule. Okay? So just be aware of that when we go on to talk about other molecules. Being able to understand that notation is important and knowing what that means, even though it's maybe not shown in a lot of detail. Same thing here. The first and linear one, that's 1, and then we got 2, 3, 4, 5, and 6. Okay, that way I can say to you, okay, so look at carbon 3 and tell me where the which side of the molecule is the hydroxyl group on carbon 3, and you would say, well, it's on the left-hand side in this case. Okay, all right. Moving on. Okay, so monosaccharides, 1 sugar unit. We also have something called a disaccharide. If you think about it, what does di usually refer to? It's going to be 2. So if we have a disaccharide, we have 2 monosaccharides joined together. Also, a recurring theme that you're going to see when we talk about these macromolecules is the types of bonds that are formed between them. So, in the case of all these macromolecules, let me start off with that. In all these macromolecules, um, they're all covalent bonds. However, you do need to know this. Unfortunately, it would be nice if you didn't have to know it, but you do. You need to know for each macromolecule what type of covalent bond it is. And in this case, if you're going between two monosaccharides, two sugar units, it's called a glycosidic linkage. Okay, it is a covalent bond, but it has a more precise name. So if you see in a prompt something about there's a molecule that scientists have discovered and it has glycosidic linkages between the monomers, and it's in a ratio of 1 to 2 to 1, carbons to hydrogens to oxygens, then you would know that most likely that would be a type of carbohydrate that has just been discovered. Okay, so I know I'm going through that fast, but since we're on a video, I feel like you'll be able to go back if you need to. If you have any questions on that, let me know and I can give you a more detailed explanation of that. All right, I think this next figure actually shows a disaccharide reaction. Yeah, all right. So I'm not going to worry too much about maltose here. That's two glucose molecules together. Each one of these is a monomer, right? And then we have a dimer here. More interesting is when you take glucose and you take fructose, another monomer, and you put them together, you get this guy here. Anybody know what that disaccharide is? That is table sugar. So we use the word sugar all the time, right? You ask, can I get some sugar for my coffee? I need a cup of sugar for this banana bread recipe. Whenever you're talking about that, you are talking about table sugar. Sucrose is table sugar. In biology, there's lots of different sugars like fructose and glucose, and maltose is also considered a sugar. But when we're talking about, simple terms, and not biology, sucrose is what we refer to as table sugar. All right, you got another picture here, another diagram, or another video that I will let you peruse on your own if you think you need to watch it. Okay, so we've had mono, di, and now the last one is polysaccharides. These are polymers of sugars, and they also have storage and structural roles. So whereas monos and dis are mainly for energy and for quick energy, when we're talking about polysaccharides, they can have a couple of different jobs depending on whether or not what their structure is, or how they're formed. So let's look at those different kinds. Starch is a storage polysaccharide. So if you hear starch, you immediately know it's made from glycosidic linkages. It's got the CH2O format, and it's going to be found in plants. Okay, it consists of a whole bunch of glucose monomers put together in a way that makes it. Got the wrong button. That makes it fairly hard to break down and makes it a very good molecule for storage. Okay, but only in plants. One thing that sometimes students mess up on is they will say, well, we have starch. No, we don't. Okay, we do not have starch in our body. We eat starch. But when we eat starch, we're going to break it down. Come on, pen. We're going to break it down into glucose, and we're going to do something else with it. And that something else we're going to do with it is our body is going to make glycogen. So the storage polysaccharide that you find in animals, as opposed to plants, is glycogen. Glycogen is found mainly in the liver and in the muscles. If I need, let's say it's 5 o'clock in the afternoon, I have soccer practice, and I haven't eaten since noon. At this point, I'm getting hungry. And so what my body will do is it will break down. Remember, breaking down of a macromolecule is done by adding in water to split the molecule. I'm going to break apart my glycogen, and I'm going to make it back into glucose. And that's going to feed my body until I get my meal, hopefully sooner than later. Okay. There are also, as opposed to storage, there are structural polysaccharides. And these are ones that are very water insoluble, and they're not used for energy. They're used just for structure. And in plants, that's called cellulose. Okay. There's a tough part of the cell wall that the plant cell wall that's made out of this chemical, this polysaccharide called cellulose. It is a polymer, just like starch, but the difference is there these covalent bonds, these glycosidic linkages, are in different locations, and because they're in different locations, that's going to give starch a different property. It makes it water insoluble. It makes it much harder to break apart than, say, starch, for example. Okay, illustrative example. Again, whenever I use the term illustrative example, I'm talking about things that if they ask you about carbohydrates on a test, and you use this particular example, you'd be golden for that particular essay prompt. So enzymes that hydrolyze. Hydrolyze is a fancy word for saying to perform hydrolysis. Okay, when you perform hydrolysis, you are hydrolyzing something. So enzymes that hydrolyze glycosidic linkages in starch only break apart those linkages. They do not break apart the linkages in cellulose because they're different. They're shaped different. It's kind of like different puzzle pieces. You can't break those puzzle pieces, or you can't put those puzzle pieces together in the same way. Okay, so starch has a certain structure, cellulose has a certain structure, and enzymes, you may remember from your freshman biology, that enzymes also have a particular structure, and each structure only works on a certain subset of molecules. So the enzymes that work on starch don't work on the enzymes that work on cellulose. Humans don't have the correct enzyme to digest cellulose. Think about celery, okay? Or the lettuce, or anything that has fiber in it. So that means that we cannot digest cellulose. So the reason that we can't digest things like fiber is because of the fact that our bodies don't have that particular enzyme. Now, on the other hand, the reason that things like cows can digest, they eat grass, right? Humans can't eat grass. We can eat it, but it's going to come out the other end. This is gross, but if you've ever had a dog eat grass, you'll notice that sometimes it comes out the other end, and it's not very digested, which makes for awkward issues that sometimes you have to deal with your dog. But on the other hand, things like cows can digest cellulose, but it's not actually the cows themselves that are doing it. It's actually the bacteria that are in the gut, in the small intestine of the cow, and that bacteria has the enzymes to digest the cellulose. So it's not actually the cow itself, but it's the bacteria. So many herbivores, cows, deer, rabbits, even all the way down to termites, have what we call a symbiotic relationship with The bacteria. The bacteria get a couple of benefits from it. They get a nice warm place to live, and they get to eat some of the food that the cow doesn't normally digest. And then on the other hand, the cow also gets nutrients from what the bacteria doesn't break apart. So both benefit from that relationship. That would be called a mutualistic or mutualism, called mutualism, when both benefit. So that would be a mutualistic or a symbiotic, positive symbiotic relationship. Here is just a diagram, and we're not going to go into huge detail on this, but each one of these, starch, glycogen, and cellulose, if you look at them, kind of the broken down part here, you can see that they have different, this one has branches on it. They just showing the little bit of the branch right there. In glycogen is branched. In starch, it's all single chain, so it's not branched. And then you also get a different, you get unbranched chains, but you get hydrogen bonds between the branches, and you don't see that in the other two. I don't expect you to understand these structural drawings. I just want you to know that because the glycosidic linkages are in different positions, that gives two things. It gives the different carbohydrates different properties, and it means that they have different functions. And like in the case of cellulose, it means that some things can break it down and some things can't break it down. So you need different enzymes for all these things because of the fact that they have different structures. Okay, so moving on to our next macromolecule, which is lipids. Lipids are a very diverse group. They are in general hydrophobic, so meaning that they really do not mix well with or at all with water. Okay, lipids are mainly made of carbons bound to hydrogens. So because there's a lot of carbons and a lot of hydrogens, we call those hydrocarbons. Lipids functions are mainly as long-term storage. So I say fats, but it's long-term storage. Also cell membranes, that's the phospholipid part, and steroids. And we'll talk about each of these in turn. Probably when you think about lipids, the one you think about right away is going to be fats. And so fats have a particular shape to them. All these guys, fats, lipids, phospholipids, and steroids have commonalities, but they're going to have slightly different structures. They're all lipids, but they have a slightly different structure. So let's talk about them. Fats are constructed from two types of smaller molecules called a glycerol and fatty acids. Okay, they are made of actually one glycerol, and they are made up of 3 fatty acids. So let me see if there's a picture here to show you that. The glycerol is a 3-carbon alcohol that's attached to the hydroxyl. You do not need to know that. You don't even really need to know what glycerol looks like. Instead, here's a picture of this is the glycerol molecule here on the left. And here's one chain of hydrocarbons. That's my fatty acid being bound by removing a water molecule. So I'm losing a water molecule to make one chain of fatty acid. But that has to happen 3 times. And we need, it says 1 of 3 dehydration synthesis reactions. So we need to do that 3 times. So the next picture actually shows that being done 3 times, if I can get my pointer to work. So here's one fatty acid, the one we saw before. Here's a second. And here's a third. So after you look at these for a while, they start to be pretty obvious. When you see those long hydrocarbon chains, if you're taking AP biology, this is your tip-off that this must be a lipid. Okay. Notice how where we are in the first one here. Let me go back one slide. We were removing water. So I told you it's a dehydration synthesis reaction, just like it was for our carbohydrates. So each case, we're going to remove a water molecule. And there's a water molecule that has been lost here. It's not showing the water. It's already gone. And here and here. These are called ester linkages. So remember how I said they're all covalent bonds that are formed? However, those linkages are different. Those bonds are different. Now they're called ester linkages. Okay, so these are covalent bonds. But these are covalent bonds for lipids. Okay. So if I said scientists found a different macromolecule consisting of long chains, 3 long chains of hydrocarbons, and that was bound to and those chains were each bound to a glycerol by way of an ester linkage, you would know that that was a fat molecule. Fat molecules are also called triglycerols. Okay, so when you talk about triglycerides, you talk about numbers on triglycerides. That's actually what you're talking about. You're talking about how many fat molecules you have in your body, or in your bloodstream, I should say, because that's what they're measuring is bloodstream triglycerol levels. Okay, this is just going to show how those come together. I'm going to skip that. Go ahead. Feel free to watch that if you think you need more help on that. Okay, fatty acids can be really long. They are usually long, but sometimes they can be incredibly long. What's more important, though, for us is that we need to focus on whether or not they have double bonds. And this is a little bit weird. Some fatty acids have no double bonds. If they have no double bonds, they're considered saturated fats or saturated fatty acids. If they have at least one or more double bonds, they're unsaturated fatty acids. Okay? And that gives those molecules specific properties. Then you've heard about saturated fats, and you've heard about unsaturated fats. So that's what this plays into. Now, what I think that students have an issue with sometimes is like, well, double bonds are stronger than single bonds. And so sometimes students will be like, well, saturated fats I know are bad for you. They tend to stick around in your body. They don't get digested. They can lead to things like heart disease. And so people will say, so saturated fats must have double bonds. Okay. And saturated fats do not have double bonds. Okay. In contrast, unsaturated fats have at least one double bond in them. Now, if you look at, let's just say double bonds. If you look at the structure, look at this one here, you can see that these chains are pretty tightly together. Okay. And that there's a little kink there. These guys are tightly together, but this one, the third one, is not. So that allows water and enzymes to get in there more easily and help break apart the molecule. So the result is that unsaturated fats tend to be easier to digest and less likely to stick around in your body and cause things like heart disease. Whereas the saturated fats over here, because they're so tightly packed together, water kind of gets repelled, tries to go in, and whoop, sorry, rejected. And the water can't get in there, and the enzymes can't get in there. And so it tends to not break down as well. So What that also means is that it gives it different properties, just like we talked about with carbs earlier. And one of those different properties is saturated fats tend to be solid at room temp, and unsaturated tend to be liquid at room temperature. So that's actually shown on the next page here. So saturated fats, fats made from saturated fatty acids are saturated fats, and they are solid at room temperature. Most animal products, animal fats, I should say, are saturated. So butter, bacon grease, those are examples of saturated fats. Things like olive oil, as well as, so olive oil would be a plant oil, or fish oils tend to be unsaturated. So in terms of your diet, you really want to have a larger amount of the unsaturated fat in your diet than you want to have the saturated ones, because a diet rich in saturated fat will contribute to those saturated fats will convert into something called cholesterol. We'll talk about a little more in a little bit. And that causes these deposits to form inside your artery. So if you got a nice round artery, nice wide artery, and you start eating a lot of saturated fats, what happens is this starts to get narrower and narrower and narrower until eventually you end up with a situation where it might be completely blocked. Okay, and that can cause heart attack. It could cause a stroke. It could also cause a piece of this to break off and travel, and a piece of that to travel and break off, and you could get a blood clot somewhere else. Okay. A process that's become less popular over the years is hydrogenating an oil, and this is where you take an unsaturated fat and you add tons of hydrogens to it. And when you do that, you create something called a trans fat, and it has lots of these trans bonds in them. These are actually, and these are man-made. These don't occur in nature. You have to work to get this to happen. Some foods, less now, fortunately, but some foods you'll see partially hydrogenated or just hydrogenated oil. And what that means is they've made those into a solid. Those are the hardest of all of these fats to break down, and more likely to contribute to heart attacks, cardiovascular disease, heart attacks, stroke, high cholesterol than any of the others. So even more than a saturated fat, trans are worse. So read your labels when you're buying foods, and be careful not to eat a lot of those partially or completely hydrogenated oils, because they are not very good for you. Okay, major function of fats is energy storage, and that's for long-term, really, energy storage. It's not for quick energy. It's not going to be, you're not going to go out and play a soccer game, and you're not going to tap into your fat storage. Okay, that is much more for long-term storage. Another function of fats, so we call it adipose tissue, is fat tissue. It also cushions our vital organs. So it is important to have some fat on your body. You don't want to completely go without fat. That actually can be catastrophic. So you want to make sure that there's some, because it will cushion your vital organs, so that when you accidentally fall or get pushed or in a car crash or whatever, your liver is going to smash against your rib cage, for example. And if you've got some fat there, it will help to cushion the body. It also helps to insulate the body too. So the more of that adipose tissue you have, the warmer you will be as well. Okay, that's it for fats. Next thing we want to turn to or talk about is something called a phospholipid. So a phospholipid is, again, we've got those fatty acids. We've got the glycerol, and then we've got 1, 2, 3 fatty acids. So fatty acid, and fatty acid. But what happens in a phospholipid is one of those fatty acids is replaced with, where'd that come from? A phosphate group. Okay, remember from your functional group quiz, your phosphate group. If you've not taken the functional group test quiz, I would suggest that you stop watching this lecture. Sorry, I should have said this earlier. And make sure that you have done that, because we're going to start using amino group and carboxyl group and phosphate group. So it's important to understand those functional groups, because I'm just going to start saying, here's a phosphate group, and you need to know what that is. Okay, so if you haven't done that, please go make sure you do that as quickly as you can before you proceed any farther. Okay, so the interesting thing about this is when you do this, let me just show you the picture because they do a better job of it than I do, obviously. Here is my phospholipid, and here's my glycerol part. Here's my fatty acid chain down here. Here's another fatty acid chain. But then I don't have a third fatty acid chain. Instead, I have this phosphate group here. Okay. And sorry, the I said that wrong. The glycerol is actually down here. Glycerol's here. But then there's a phosphate group attached to it. And that phosphate group, PO4, is interesting because it is hydrophilic. Phosphate likes water. As opposed to these little guys here, these my long chains, these are hydrophobic. These fatty acid chains do not like water. Okay, so it creates this unique situation where a phospholipid is actually part hydrophilic and it's part hydrophobic. Just erase that here. Okay, so you've got the two fatty acid chains that are hydrophobic. And then you've also got the phosphate group, but it's hydrophilic. Okay. Sometimes we call the top part that's got the phosphate head, we call that, or phosphate area, we got to call that the head. And we call these guys down here, we call these the tails. When you look at a cell membrane will try to orient itself into two layers, a top layer and a bottom layer. So here is, this is a cell membrane here, or it could be a cell membrane. And I've got water here, so that could be the inside of the cell. You could say in and water. I've also got water outside. Remember, we're about 60% water. So there's going to be a lot of water in our body. So those tails have to do something about the fact that they are hydrophobic. These are our fatty acids. And so what do? They stay inside. They stay as far away from the water as possible because they are repelled by them. But then you've got these areas on the outside, and then the inside and on the outside. And these are the heads. These guys are hydrophilic, and these are the phosphate parts of that phospholipid. Okay. So long story short, this creates a unique situation because cell membranes can keep things out because of the hydrophilic and hydrophobic interactions. But, cell membranes work to only let certain things through. And we're going to talk more about cell membranes in Unit 2 and how they do that. So when phospholipids are added to water, they form double layers called bilayers. At the surface, phospholipid is arranged into a bilayer. The hydrophobic tails are going to be pointing inside. Where did I go? That was a sad face. I think I hit Control Z one too many times. There we go. So the hydrophobic heads are going to point inside. So they're going to point towards the interior. And then you're also going to have the hydrophilic heads, and they're going to point to the outside. All right. Our last fat is a steroid, and I think we'll stop after there because we've gone, I think, about as far as we should right now. We're probably full up with information at this point. So let's just talk about steroids. Steroids are also lipids, and they are characterized by 4 rings that are attached to each other. So these 4 rings. A very good example of steroids is cholesterol. Cholesterol is a type of steroid. It is found in cell membranes. It is important in cell membranes. It is also the precursor for other steroid molecules. So you need cholesterol in your body. People say, well, I have high cholesterol. Well, that's not good. It's not good to have a high level of cholesterol because that can contribute to heart disease or cardiovascular disease. However, you need cholesterol. You need it in your cell membranes. You need it for other steroids as well. So it's having a happy balance of it, and not that I shouldn't have it at all. Again, here's a picture of steroid. This is cholesterol, and notice how it has these 4 rings. They're all attached to each other. Okay, if you see that 4-ring structure like that, you know you're dealing with a steroid. Okay, you don't have to know the ins and outs of this diagram. You just have to remember that there's those 4 rings. If there are those 4 rings there, you know that that's a steroid. All right, I think that is as far as we'll go today, and then hopefully you just check and see if next time, we still got a lot of slides left. We'll see if next time we can get through this. Oh, it looks like some of these are repeat, so we should be able to. Okay, so at this point, you should be getting through the syllabus, or not the syllabus, the study guide. See where we're at here. Should be getting through. You want to get through here, through lipids. Okay, so work on this. Make sure that you have answered all these questions in this section and you've read through section 5.3. And once you've done that, then proceed on to the next part, which will be on proteins and nucleic acids. And I think proteins take a while, so that's why there's so many of them. Yeah, so we've got proteins and nucleic acids left. So have a good day, and I will talk to you soon.